Okay. So can you see my screen now, please?
Yes.
Yes, we can.
Okay. So the first thing is, so you said everything you need to know to start coding your own shell. So basically, this is actually everything that you actually need to know. Every other thing, every other thing that you are going to implement would be logic. Every other thing you're going to implement will be logic, but this will be the foundation of what you need to understand. So I want us to just take this one after the other and try to understand what it is and what exactly they are talking about. So the first thing is PID and PPID. So let's unmute our mics. What do we understand by PID? What is PID? What is PPID? So guys, what is PID? What is PPID?
PID is process.
So okay. So a PID, there's a definition here. A PID is an acronym for Process Identification Number. So excuse me, on a Linux or Unix-like operating system. So a PID is automatically assigned to each process when it is created. So a process is nothing but a running instance of a program, and each process has a unique PID on a Unix-like system. The easiest way to find out if the process is running is ps aux command and grep the process name. If you got an output along with if you got an output along with the process name, then your process is running. So that's just how to get the process name. So let's run this. Let's do a man. Let's man ps. So ps. Let's just check the manual page for ps. So ps displays information about reports a snapshot of the current process. Okay, so ps displays information about a selection of the active processes. If you want a repetitive update of the selection and displayed information, use stop instead. This version accepts several kinds of options. Okay, let's just, so depending on the system, Unix options, BSD, GNU options. So let's just see the options we have. So this is AXU. See every process on the system using the BSD syntax. So see every process using the standard syntax. EF. So I want us, we can open our systems and try to, you can type in these commands and then let's see what it brings out. So you can open your system and try this, please. So let me open another tab here. So let's first try PS AUX. So this has a lot of information. So we can see that it's displaying the PS and the PID. It's displaying the PID, and there is one here that has a PID of 1, which is the init. So this has a PID of 1. I'm trying to get, there is a command that will also give you both the parent process too. Let me search that online. Guys, does anybody remember that command that will show the PID? I don't know if you've come across it. It shows PID and PPID. Let me see if we have something here. PID, to say a process is undefined. PO, PID.
It's PS and
Okay.
then the flag AEF.
AEF. Okay.
Yeah.
So bit long. Okay, very good. Very, very good. Okay, guys, so we can see it here. So the PID is the program's process identifier. So just like every time you open a file, I don't know if you did yesterday's task, every time you open a file, it will give you a particular number, and that number would be used to identify the file. Can we remember that? So initially you have three files that are opened, 0, 1, and 2. And those are the files you use, your standard input, standard output, and standard error. So those files were already open. So any other file you open, it will give you a unique file description number for that particular file so that you can operate with that file. So the same thing is also the same concept with this process identifier. So every process that starts is going to have a PID. Now, that process, if that process was started by a process, if that process was started by a process that is already running, it will have a parent process identifier. So this is the PID, this is the parent process identifier. So you can begin to appreciate some things on your computer. There are two processes here. There are two processes here that don't have a PID. Their PID is 0, which means that they were started when your computers started. They were started alongside with your computer. So, and they have the PID of 1 and 2. So the init process is the first one. You're now seeing another one here, the K thread. So maybe on your own you can check what these processes do. Then from there you now begin to see that all this either of these two processes will begin to start up some other processes, because if you check this PID now, if you check the PPID, sorry, you see 00, then you are seeing the next one, the RCUGP here is the parent ID for 3. So process PID 2 becomes the process ID for 3 all the way to 230. Then you now see these ones being born from 1. Then you see 1122 and all of that until you get here. So you're seeing that this was started by another 797 here on my own system. I don't know what will be on your system. Was started by another running process. So basically what is happening is that, for us to understand, is that processes can give birth to other processes. That is just what we need to understand. A process can give birth to another process. So that's why you have the concept of parent process, you have the concept of child process, parent process and a child process. So what do we need this for? Why do we need this? Why do we need this? Remember, you're going to be you want to create a shell program, and your shell, the purpose of your shell is to run commands. And those commands that will be run by the shell will be processes on their own. For you to run your shell is going to start a running instance and will have a process ID. Now, for every program that your shell is going to run, those programs too will have their own process ID. But your shell will become their parent process ID. I don't know if you understand that. Do we understand that, please?
Yes.
Okay,
Yes.
so if you check on my own PC now, I have two instances of bash running. This is the first one, 35501. There's another one here. Sorry, this is the parent. I'm checking the parent ID. 35519. There is another one here, 36081. But the two of them have the same processing ID, the same parent process ID, 35501. This one too, 35501. So what is 35501? I'm using an Ubuntu system. So this is the process that has 35501. And then you are saying that it is the GNOME terminal server. So of every instance of bash that I open directly from here, if I add a new one, if I add a new tab now, a new processor, and then I type the same command, PSELF, then we have a new bash instance here with this PID, and then the parent processor ID is still 35501. Now let's say I run a program. Let me run a program from here. Let me run VS Code. So VS Code is running presently. So by the time I rerun PSELF, so you can see here, now I have code. So that's for the VS Code. I have code running. And so this is a bit. I want to choose a simpler program.
I think maybe it's because of the flag you used.
There are so many things on code.
Yeah, usually VS Code runs a lot of programs.
Yes, it runs a lot of programs. So I want to choose let me look for a simpler program. Let me close this. Which simple program can I have running? Okay, let me say I start Vim.
Try B.
We have an instance
It's
of Vim
simpler.
running there. So let me rerun this program here. ELF. Okay, so you see we have Vim here. So this is the Vim VI. It's running here. This is the process ID of the VI. Now this is the parent. The parent is 36169. That's the parent. Now, if you check 36169, you see it's bash. And then the parent of that bash is 35501. So 35501, 35501, which is the GNOME terminal server. So basically what is happening is that in your computer, there is a process tree. There's a process tree. One, there is going to be a parent tree, another parent tree gives birth to other processes. From what we can appreciate from this so far is that when you start your computer, from what we can appreciate here so far is that when you start your computer, there are going to be two parent processes that will be created with PID1 and PID2. And then from this PID1 and PID2, other processes are given birth to. You can see 3 was born from 2. So other processes are given birth to. So there are going to be two parent processes. And then from those parent processes, you have a tree of children processes that will be born from there. And the next thing is you have your computer running. So that's basically what has happened. So said this process ID is used by many functions and system calls to interact with and manipulate processes. In order to retrieve the current process ID, you can use the system call. So there is a system call called getpid. Let's see the manual page for getpid. Let's see the manual page for getpid, and let's see how to use it. So man getpid. So there are two things that we can see here. Number one is get PID, and if you check exercise 0 here, you'll see get PPID. So get PID, get PPID. So they are sister functions, and they are, what they do is they get the process identification. So of course, if you want to use them, these are the header files that you need to add. The sys types .h and unistd.h. And these are their prototypes. So PIDT. So a process identification number is a PIDT. So a PIDT is a type of a small integer. It's a type of a small integer. So you can still also say int equals to get this thing. Just understand that a PIDT is a type of a small integer. So their description. Get PID returns the process ID. That's the PID of the calling process. It returns the process ID of the calling process. Remember, what is a process? A process is the instance, the running instance of a program. When you create your program, maybe you write a particular program and you compile it, it is not yet a process. But the moment you run that program, it becomes a process. Do you understand? So what happens is that it is an instance of your program that runs. It is not the program itself directly. How do I put it? If I come here, let me quit this. Let me just use. Sorry, these days I think I prefer working directly on VS to save myself some time. Or let me do this here. Are you recording? So I prefer to use Emacs. Okay. Let me cut. So I have this program here that's just printing something. Let me see if I can edit it. I just want to print hello. That's all. So if I take this program now and I compile, okay. So if I do ls, you would see the program here. You will see this hello. That's the program. Now, when you want to run a process, when you want to run a program, what happens is that your computer will take this program and copy it into your memory. So your computer copies it into your memory, your RAM. When it is copied into your RAM, sorry, excuse me. When it is copied into your RAM, it becomes an instance, a running instance. So the computer is not running it directly from your hard disk. It doesn't run directly from your hard disk. It first gets copied from your hard disk into your RAM. That is why if you are running any program, maybe, for example, you try to run a game, you want to play a game on your system, a heavy duty game. You are going to see that game has it has requirements. One of the requirements would be that your RAM must be of so size. The reason why it is demanding that your RAM should be of that size is because it needs to copy some particular, it needs to create some particular instances of that game. And that instance will be created in your RAM. So the computer will copy this and copy it into your RAM. So that now becomes the running instance. So it will now attach a process to it. That is why this same hello, I can run it. I can have several instances of it running, and there will be no problem. That's why if I do this, if I still write here, if I check, as our PS, this thing, if you look here, you'll see that we have different instances of bash. This is one instance of bash. This is one instance of bash. This is another instance of bash. I think I created 3 instances, if I'm correct. There should be 3 instances of bash running. Bash. This is the 3rd instance of bash. And if I do which bash, you will see the location of bash. Let me just cd. I want to cd into this location. So this is our bin directly now. Directory. You will see bash run a bash inside here. So you can see this is bash. So this is bash. So bash is a program on its own, and it is there in your hard disk. So every time you are running this process of bash, what happens is that a new instance is copied into your memory, giving an identification number, and then it runs in your memory. So all these things are happening inside the memory. So that is why it is called an instance. So an instance is that program, your program copied into memory and then begins to run. That is an instance. So what the, I believe we were here. Okay, not here. Yes, we were here. So it returns the process ID, that's the PID of the calling process. So this is often used by routines that generate unique temporary file names. So the get PPID, which is the sister system, returns the process ID of the parent of the calling process, of the parent of the calling process. So this will be either the ID of the process that created this process using fork, or if that process has already terminated, the ID of the process to which this process has been reparented to, either init or sub-reaper process, defined via PRCTR2. We can, or PR set child subgroup. Let's just leave all that for now. We don't want to deal with this. So what this is telling us is that the PPID can change. That's the parent processing ID can change if the parent process has already been terminated. So a child cannot be without parent. If this child terminates, if the parent has already terminated, what would happen is that the init process, most of the time, the init process, which is one, will now become the parent. The reason for that is that something must be available to terminate that process when that process finishes. So a parent process is supposed to kill a child process once the child process has finished running. But I think there is something I've not really had time to read so much about it, called zombie processes, which you can have. I've not really had time to read much about zombie processes. I think I will need to take time to understand what zombie processes are. But for now, from what I know is that something must be available. So if the parent process, that's the process that started a particular process, if that process has terminated, the init process will become the parent process, unless you have another setting in place for another process to take over the child process when its process dies, when the parent process dies. So let's see how these functions work. Let's just demonstrate these functions. Let me still use you. Okay. So remember, what we want to do is we want to test this out. So we will need two header files. We will need these two header files, so we can just copy them over. So we use PIDT. I equals, let me use PID equals getPID. And let's do PIDT. Okay, so we have our file created here, PID.c. So let's run it. So we are saying that the PID is 36635, and then the PPID is 36169. I want to have a system call. There's a system call called sleep. I want us to use it in this. So the sleep function in C returns 0. Okay. So I just want to set a timeout. So you use the sleep function to set a timeout. I want to set a timeout. So I want to delay the execution. I want to delay the execution of our program. I want our program to run there for a long time. So maybe I'm going to make it sleep for like 30 seconds so that we can see the PID and the PPID. Sorry. So we can see the PID and the PPID in operation. So let's go back to that program. So we'll have we'll call a sleep here. Before the program terminates, so let's sleep the program. So let's sleep for 30 seconds. So we already have the UniSTD here. So let's save this. So you can see it printed. This is it now. The program has not yet terminated. So if I come back here, let me use this. Let's quit. Let's do our PSELF. So we have this is the A.out here. Can you see? So the A dot out is, this is the PID 36784, and this is the parent. So the program just terminated now. So 36784 and 36169. Three six seven eight four and 36169. So these are program here. So we can appreciate the PID, and then we can appreciate the parent. So it is this 36169. What is 36169? If we look at our process table here, 36169. 36. So 36169 is a bash. So it's a bash process. So this bash, which is this, so this bash was the one that called the process. So that bash was the one that called the process. Do we understand, guys?
Yes, sir.
Yes, we understand, but I have a question.
What's your question?
Now, since bash is the process that called this process, if we end the bash, we end the child process, or the child process will continue to run in the background.
Okay, so let's see. I think let's see. I want to see how to use. There is a kill command. So I want to kill a PID. So it sends a signal to a process. Kill options PID and that. So the description is so let me see. So Q9, all processes you can queue. Okay, no. Here, transist number 11 to a signal name. Okay, let me see if I can understand this. So use Q to terminate a process. So kill the process once. So this is the command we need. So Q9 and process ID. That is what we want to use. This is the command we want to use. Q9 and process ID. So let's go back here now. I'm going to make this program run again. How do I do it? Let me try to extend. I want to try to extend the time. Let's give it like 50 seconds to run. So we run and we compile. So let's run it. So this is the PID. This is the process, the parent process ID. So I'm going to copy this. Then I'll come here. Q 9. I'll paste that. So we have killed the parent. So let's rerun our PSELN. So okay, right now, do you know what happened? When we killed the process, we also killed the parent. We also killed the child because it closed that terminal. Do you understand? It closed the terminal we were working with. I will demonstrate that when we start talking about fork. Do you understand, Mr. Abdullah? Mr. Abdullah, can you hear me? Okay, what I can do is let's just quickly have a jump to fork. Just quickly visit fork and come back. So if I come here, I'll just write a code. If you don't understand fork yet, we will talk about it later. But let me just write a code. Emacs PID.c. So if I come here, I'll use fork. Still PID. So let's just call it I across to fork. Okay. So I'm going to sleep the child process. I'll sleep the child process. And then I'll allow the parent process to execute normally. Let me put it this way. Sorry, excuse me. Okay. So let me just explain this code before we run it. So what is happening is that I don't think we will need this anymore. I don't want to use this get PID and all of this. We don't need this presently. So I can just puts. So program started. Okay. Maybe one way we can appreciate this is let's print their PIDs. or better still, if I want to print the PID of both of them, I can just do it once here, because after fork, anything that after fork will be done in both the parent and the child process. So we'll print the PID and the parent's PPID. Okay, so our program is going to be of this. So we are printing program started. Now immediately we will fork. Now anything that happens out after fork will happen both in the parent, because fork is going to duplicate the program. It's going to create a child process. So all the codes afterwards will both run in the child process and the parent process. Only if you specify conditions, and those conditions will be whether they run in the child process or in the parent process. So here now we would have, I'm saying that this first code to print the PID of the present process and the parent PID of that same process using getpid and getppid. Then we would also say if so this, the return value of this fork now. So if it is equal to 0, usually fork will return 0 for the child process. If it's equal to 0, so you print I am the child process, and then the child process will sleep for 50 seconds. So that means it's going to continue to execute for 50 seconds. And then in the parent process, it's also going to print I am the parent process. And then it will return. So this is what's going to happen. Let's compile the code. Why do I have some reds here? Why are you red? So let's try to compile this. So our code is running well. So you can see this for the parent ID. For the parent ID, the process is 36985, and then for the child, the parent is oh, sorry, I made a mistake there. Trying to see something did not print. It did not label I am the child, I am the parent. Let me quit this. Something I wanted to why didn't it do that? So program started. That's interesting. Sorry, just a minute. Anybody knows why this thing did not print?
Or maybe you should try using printf.
That's what I want to do.
Sorry, I just joined like a few minutes ago. That 50, is it like 50 seconds?
Yes.
Okay. I was thinking maybe you should reduce it so that you can test your stuff without waiting for a whole minute.
No, I can always quit it.
Okay.
I can always quit it. So the same thing is still not printing. It's still not printing. But anyways, but we can see it here. This uh, our code has exited. But let's first see something here before we go on. In the parent, the PID is 3708. And the parent of that parent is 36906. In the child, the PID is 37029. And the parent of that child is 37028, which is the parent. Do we understand? That's the PID of the parent. So 37028, 37028. So the PID of the parent is the PPID of the child. So why is it not sleeping? So this is supposed to sleep.
Can you try running a printf outside of the well, I think you already have a printf outside the if. That's I equal to 0.
This one
Oh,
here.
okay. Are you making I equal to 0 or yeah? That first I equal to 0. I equal to.
Thank you, thank you, thank you. That's the problem. I believe that's why the code wasn't working. Let's see. Okay, so we can see I am the child process, I am the parent. So the child process is still running. So if I come back here, this is our a dot out. So which one is this? 2785. Two seven two eight five. So in this situation now, 27285 is, this is 27285. Oh, sorry, I think that's the parent. 27285. This is 27285. So 27285 is the system D. That's system D. So this one is what inherited the child. This was what inherited the child. So that means before, sorry, if I come back here, you see that this PPID here was not printed, was not printed as the parent. It was not, it's not 37106. It means this died. The parent died here. The other this computer ran this was that the parent already exited before the child exited. So let me see if there is a way we can tweak it so that we'll have the parents wait a bit before the child also dies out. We'll have the parents wait a bit, maybe like the parents will wait for like 20 seconds and then the child will wait for 50 seconds. So let's put it here, sleep. So this will sleep for, you sleep for 20 seconds. Okay, so you can see the parent processing ID of the child now is 37147 because the parent is not yet dead. This is the parent. The parent is not yet dead. So if we come here, we will see the two of them running together. At this moment, the parent of the child is recorded as this one, and then this is the parent of this. So one of them has, I think both of them have terminated. Let me see, I think one of them should have terminated by now. If we rerun this, the parent has terminated. So in this case now, the system MD again becomes the parent of the child. So I think what is happening is that if you run this inside your sandbox, or if you run this inside Vagrant, what will become the parent should be the init. But because I'm using a graphical user interface, I'm running Ubuntu. This is Ubuntu. This is the Ubuntu system. So what is set? Where did we read that? I think we read it from here when we did man get PID. So it says returns the process ID of the parent of the calling process. This will either be the ID of the process that created this process using fork. initially, which was the process ID of the program, that's of the parent of that in our program. And then if that process has already terminated, now when our parent process terminated, says the ID of the process to which this process has been reparented. So the process was given another parent. That child, which was waiting for 50 seconds, was given another parent. So it is either the init one, so that's the first process, it's either the init process, which has the identity or the identifier of one, or but in this situation, it's not saying it has the identifier of one. I think this is just for, this is how you would read the man page for init. That's why it's giving you the bracket one, or a sub-reaper process defined via the printctl, the so pr set child sub-reaper. So I think if we man, I think that should stand for parent control, prctl. So it manipulates various aspects of the calling thread or process. So anyway, it's not
Okay.
anything for us to use, but they're just trying to tell you that you can set who becomes the parent of a child if the parent, the current parent of that child, terminates before the child, using this system call. So it's a system call on its own, but we don't have any business using it. But what we need to take home is that if the parent of a particular process dies or terminates before that process, then it would be given another process. Usually it will be the init, but because it's a graphical user interface, so the parent process becomes the system MD32725. Where is it here? If you are running the sandbox, you can try this on the sandbox, please. So this is the process that now becomes the parent, which is the lib system D. So system D, and then under the user, because this is more of a graphical user interface. Let me see if I run this. Should be terminated already. If I do sudo, I want to run as so now we are running as root. Now let me see if I try to run. Okay. So I just want to try something. So the parent is still running. The parent is still running. Parent is still running. The parent is dead. So it still goes back to this. So I think what is set here on this system, the graphical user interface, is for the system D to take over, to become the parent of any orphaned process. So that is what is set here by default. But I think we understand the concept of parent ID and PPID.
Yes, sir.
Please, can you open the code? I want to try it. I want to try it on I have a grant here.
Okay.
All right, so just give me a minute. Let me put it up.
Okay.
You can as well take a screenshot if you want.
I just want us to test it. Not really that.
Okay.
Put program started. But this is being recorded, ba?
Yes, it is.
Okay, because I didn't join from the beginning, so I don't really understand a lot of the things happening here, but I'm just trying to follow up. Printf PLD dash percentage D /new PPID dash percentage D /new line close that get PID get PPID if I is equal to 0 printf and the child process new line sleep 15 if I is not equal to 0 sleep 20 printf and the parents process it now new line come on close okay return wait but this your second if statement it doesn't have the if doesn't have a closing.
Because the sleep 20 terminates it.
Oh, okay,
So
so
that
doesn't need
colon ends.
okay. So it doesn't need that okay
Okay. Okay. Sorry. It does actually.
okay
It does.
because it's if it's since we still have printf under the if.
Initially, I didn't put sleep. I think that was where the error. I didn't
Yeah,
include sleep.
sleep before. Okay, so I think I'm good. GCC PID.c. Okay, dot a dot out. Oh, okay. Yeah, I'm done with the text. Like testing the task terminal. So what's the reason for listing that listing again? For listing the processes?
Yes.
PS, just PS. I think without
Yes.
ELF.
With ELF.
Okay. Okay, so I want to run it now. It's running PS ELF. Okay. So I have to e dot out. So it's currently running and the parent and I'm waiting for it to stop so that I can see where the child takes coming PS.elf. Okay. I think the parent has stopped now. It's giving me an address of 1.
Yes. It will give you an
Yeah.
address of.
Yeah, so it's 1. In it, yeah, exactly. In it. So I think I can share a screenshot. So that is
Okay. Please
on
share.
it.
Appreciate it.
Yeah. Uh, is running down. How do I make the screenshot? Okay. I'm connected on my phone, so I'm not able to share my screen. I'll just like send the screenshot to the group. I'll copy it to my phone and then share the screenshot to the group because my system is low.
Right.
So I think we can continue while that is.
Okay, let's continue. So that's it for the parent, the PID and PPID. So of course, our next exercise is write. Okay, here it says write a program. Write a program that prints all arguments without using AC. Write a program that prints all arguments without using AC. So I believe what this exercise wants us to appreciate is that normally when you do int main.c, sorry, I want to break the recording. So just give me a minute. Let me break the recording here. So let me first stop this.